Here are all the rules for differentiation. Probably one of the rules that gets used the most is the power rule. And in order to use the power rule, you do want to know how to simplify exponents with algebra techniques and how to convert from radicals to exponents. So for example, what I mean is if you have something like 1 over x to the fifth, you can rewrite this as x to the negative 5. That's not using the derivative rule. That would be how you might write the expression so that you could then apply the power rule. If you have something like, let's say, the 7th root of x to the 9, this can be rewritten as x. The 9 stays the exponent, and if there is a radical, that becomes the denominator. So again, we haven't applied the derivative rule at this point, but that's how we would rewrite that expression so we could apply the power rule. And then in general, I mean, anytime you have something like a square root or a cube root, you would write it as a fractional exponent where the denominator is actually indicating the radical or the root in either case. And you can even have radicals in a denominator. So for example, if you had 1 over the cube root of x, you could rewrite that in steps as 1 over x to the 1/3, which would be converting it from the radical to the exponent. Since it's in the denominator, you could then rewrite that as x to the negative 1/3. So this is just to show how you might want to rewrite your expressions before you try and apply the power rule. So product rule is what we use when we have two functions that are multiplied together, where the quotient rule is the rule you would use when you have two functions that are one divided by the other. The chain rule is basically saying that you can use the regular rules for differentiation even if there's something more complicated in your expression, but then there's this extra piece of multiplying by the derivative of that more complicated piece. So let me try to show a quick example of what I mean. And it's kind of based on even what I had above there, which is that, okay, well, before we had square root of x, a more complicated thing might be something like square root of 5x minus 9. So the idea is that if you recognize that outer function of being a square root, and that you're basically dealing with that same type of problem, but this inside part is more complicated, that's when you apply the chain rule, which is where you look at the outside part, in this case the square root, and you take the derivative as though it were square root of x, and then the extra step is to multiply by the derivative of that more complicated piece, or that inside piece, which in this case would be the derivative of 5x minus 9. I know I'm not exactly going over the example now, but I will go over an example, a couple of examples of how to use the chain rule. So also here I have the exponential rule and the logarithmic rule, and then also these extra exponential and logarithmic rules. And really I just want to mention that that's actually just the chain rule again. So you really don't need to know those as being a separate rule. It's actually just applying the chain rule to an exponential function and applying the chain rule to a logarithmic function. Okay, so let's go look at some examples. Here's the first example. So this is one where I have different expressions that are added. They could be subtracted together, but in this case they're all added, but they're all separate, which means I can take the derivatives separately, so I don't need to use anything like a quotient or a product rule, for example. But if I am going to take the derivative, I want to rewrite all of those pieces with radicals or exponents so that they're written to be just something like x to a power of n. So before I take any derivatives, let me rewrite things first. So in this case, the 19 over x cubed can be rewritten as 19x to the negative 3. So if you have an exponent in the denominator, you can actually rewrite it. A mathematical notation way to rewrite that would be x to the negative 3rd, where it's no longer in the denominator and it means the exact same thing. Plus, x, where we have the cube root and an exponent of 5, could be rewritten as x with a fractional exponent. So the regular power or exponent goes in the numerator and the radical goes in the denominator. And then the other two I'm just going to leave alone. So again, I've just rewritten the expression, but I haven't taken any derivatives yet. But now I'm going to go ahead and take the derivative using pretty much the power rule. So 19x to the negative 3, if there's a coefficient in the front, you can just leave that alone, but then take the derivative of x to the negative third. So the power rule says to bring the exponent to the front, x, and then the exponent gets reduced by 1. So I'm going to subtract 1 there, plus bring the exponent down for the next one, which will be 5/3 x, and then now the new exponent becomes 5/3 minus 1, plus, you might know this derivative as just being 9. So the derivative of 9x is 9. The reason is that x is actually the same thing as x to the 1. So if you apply the power rule, it becomes 1 x to the 0. And then the derivative of 7, or the derivative of any constant by itself, is 0. So let me go ahead and simplify and rewrite our derivative. The first expression is negative 57x to the negative fourth plus 5/3 x. And then when we have fractional exponents, you want to keep in mind all the rules for common denominators, because they'll apply. So 5/3 minus 1, we could get a common denominator by multiplying it by 3/3, so that becomes 5/3 minus 3/3, which is 2/3. And that's our new exponent. And then plus, for the derivative of 9x, I used that power rule there, but again, you might be familiar with that. If it's just an x, then it basically goes away and you're just left with the coefficient. But if I did write it this way using the power rule, x to the 0, anything to the 0 is 1, so that becomes a 1, leaving just the 9, and then the 0 I just leave off. And this is our final answer here. Oh, I actually am, before I highlight this and say it's the final answer, I want to mention that at least the instructions given here are to write it with no negative exponents and no fractional exponents. So basically this means we have our answer. It's kind of converting it back to that form that it was originally in. So I'm going to go ahead and do that as the last step. So negative 57 x to the negative fourth, I'm going to move the negative x to the negative 4 to the denominator and rewrite that as negative 57 x to the positive 4 plus 5/3, and to not have a fractional exponent here means I need to convert it back to a radical. So this would be times the cube root of x squared and then plus 9. And this is our final answer. Depending on how much you've done derivatives already, this might seem obvious to you after a while, because using the quotient rule, lots of times it's pretty straightforward. It's if you have a fraction, and basically if you have a fraction where the numerator is some expression in terms of the variable, in this case x, as well as the denominator. And we can't simplify this because the denominator is an x plus 2 in this case, so it's not like I could split it up to be two separate fractions. So at that point then we use the quotient rule. So you can look back to the rule that was on that previous page. Basically, whenever I do the quotient rule, the first thing, that habit for me is the first thing I do is just rewrite the denominator, but write it in the numerator. So in this case, I'm going to write it as x plus 2. And the reason that helps me is that once I rewrite that in the numerator, it helps me with that pattern, because basically you're multiplying together the original plus the derivative of the other, and this helps me keep track of that. So since I have the original denominator, now I need to multiply by the derivative of the numerator. So the derivative of the numerator, well, 2x cubed, we've got 2 times, that's going to be 3x squared, and then minus 5. The quotient rule is always subtraction, where the product rule is addition. I mean, you could think about that as, maybe the product rule with multiplication. Usually you're getting a bigger number when you multiply, so you can think about that as being the addition, versus the quotient rule, when you divide by something, you end up getting a smaller number. So maybe then that's why you would use the subtraction there. So if you're trying to memorize the derivative rules, it's good to just kind of think about little tricks like that to help you out. Okay, so anyways, to keep going, now I'm just going to flip it and do the opposite. So instead of it being the original denominator, now I'm going to put the original numerator, which is 2x cubed minus 5x, and then I multiply by the derivative of the denominator. So the derivative of the denominator is just 1. And that goes all over the original denominator squared. So this is the derivative, but we would want to simplify it some. So let me go ahead and do that. Usually, what I see most with the quotient rule is people are okay knowing to use the quotient rule and starting to use it, but a lot of the issues actually come from really the simplifying, because you really have to keep track of all your steps. And, one wrong negative sign, it just throws off the whole answer. So just really be careful, take your time, and try to write down all your steps would be the advice I would have for that. Okay, so x plus 2, I'm just going to rewrite that other parentheses part. So we've got 6x squared minus 5. And I'm just doing a lot of rewriting here, kind of just because I'm simplifying one thing at a time. And then I'm going to leave off the 1 because it's just a 1. So here, if I wanted to keep simplifying, I would go ahead and FOIL this first part. And I'll rewrite my problem as I do that. So let's see if we FOIL that out. We've got 6x cubed minus 5x plus 12x squared minus 10. And to simplify, this is a place, again, where it's easy to make that mistake, is because that whole second part gets subtracted. So you really want to keep parentheses around it until you go ahead and distribute that negative. So if I drop the parentheses, it's going to end up being negative 2x cubed plus 5x all over x plus 2 squared. So there's a lot of terms in the numerator, so looking for like terms. Let's see here, we've got a 6x cubed and a negative 2x cubed that we can combine together. And it looks like we only have that one x squared term, but we do have a negative 5x and a positive 5x that will cancel out. So rewriting that, we've got 4x cubed plus 12x squared minus 10 all over x plus 2 squared. And that is our final answer. When you do apply the quotient rule, there's really no need to multiply through the denominator, because if anything, you would want to try to factor the numerator to see if something would simplify and cancel. It's not going to happen in this case, so we would just leave it like this and say that this is our final answer. Now let's look at the next example. So this is one where I would want to rewrite it a little bit before I try to take the derivative. And so what I would do here is recognize that just like if I had something like 7 over x to the 5th, I would want to rewrite that. And taking the derivative is going to be really similar, but this one has a piece that's more complicated inside here. Since it's not just an x to the 5th, it's 2x plus 9 to the 5th. So that tells me I'm going to take the derivative like I would take the derivative with x to the 5th, but I am going to need to apply the chain rule. So if I had 7 over x to the 5th, I could rewrite that as 7x to the negative 5th. So for our actual problem, I could rewrite that function as 7 times 2x plus 9 to the negative 5th. So to take the derivative, try and see like that outside piece of if I had just 7x to the negative 5th, I'm going to start the derivative that exact same way. So let me start to write the derivative now. F prime of x is equal to 7. You just leave the coefficient right in the front, times, and now this is when we would bring the exponent down, negative 5th times 2x plus 9. Don't make any changes to the inside there, and then it ends up being negative 5 minus 1, and then it is the chain rule part. This is the extra part, which can be easy to forget. And so since this was more complicated, our last step is to multiply by the derivative of that. So the derivative of that is 2 plus 0, so I'm just going to write that as 2. So this is kind of where I wanted to emphasize it. That's where we're using the chain rule. So let me try and rewrite this a little bit. So the derivative is equal to 7, and then in here we've got negative 5 times 2x plus 9 to the negative 6 times 2. To simplify, you're not going to do anything with that inner parentheses here, because it has an exponent of negative 6, which means you can't really multiply it with anything else. But here you've got 7 times a negative 5 times a 2, so you would want to combine all those together. And that would be negative 70 times 2x plus 9 to the negative 6. And if you want to write your answer with a positive exponent, we can go ahead and take that one step further and say that's negative 70 over 2x plus 9 to the positive 6. And that's the final answer. Now let's look at another problem where we would use the chain rule. And just like the last example, this is similar to if we were taking the derivative of square root of x. It's just now that inside part is more complicated than just a single variable. So the first thing we'd want to do is to rewrite it as an exponent, as a fractional exponent. So square root of x is x to the 1/2. So for our actual problem, before we take any derivatives, we could rewrite it as 5x minus 1 to the 1/2. So now that it's written in the form of like a base with an exponent, we can apply the power rule, but we're also going to apply the chain rule as well. So to take the derivative, we'll work on the outside part, kind of like just the x to the 1/2 part, and use the power rule. So that's going to be to bring down the 1/2, and normally it's just an x, but now for our problem, the x is instead 5x minus 1. And then the new exponent is going to be 1/2 minus 1. And now this is when we need to apply the chain rule. The last step is to multiply by the derivative of the inside. So here, the derivative of 5x minus 1 is 5. So rewriting our derivative, we've got 1/2 times 5x minus 1. The exponent, if I kind of show the work here, we're going to use common denominators. So 1/2 minus 1, common denominator of 2. So you get 1/2 minus 2 over 2, which is negative 1/2. Times 5. And so here, in terms of multiplying, I can multiply the 5 and the 1/2 together, but the 5x minus 1 I would leave alone because that has an exponent of negative 1/2, so I can't combine it with anything else. So rewriting that would be 5 over 2 times 5x minus 1/2 to the negative 1/2. So now if I go a little bit further in terms of how to write my final answer, I could get it to be with only a positive exponent and no longer a fractional exponent. So first I'm going to take care of the negative exponent and rewrite that as 5 over 2 times 5x minus 1 to the positive 1/2. And then changing that to a square root, it would be 5 over 2 times the square root of 5x minus 1. And that's the final answer. Now let's look at a function with a natural logarithm. So if it were just ln of x, the derivative of that based on the rule is 1 over x, which is just 1 over that argument of ln of x. So for this one, we would start by doing the same thing, which is 1 over the argument, which is x to the 4th plus 5. But this is again a place where we would also apply the chain rule. So instead of having an x, we have the whole x plus 4th. So the last step would be to then multiply by the derivative of that x to the 4th plus 5, which is 4x. And I'll just write it as a cubed here, which is 4x cubed over x to the 4th plus 5. And that's why the rule from the first page, here's the derivative for what's called here the logarithmic function rule, which is basically just applying the chain rule to the logarithmic rule. So I first just said, well, whenever it's the chain rule, I just multiply in the end by the derivative. And in this case, they're just putting that derivative in the numerator. So that's what the g prime x in the numerator is indicating. Now let's look at this last example. So there's a few different rules we have to use in this one. We're actually going to end up using the power rule. We're going to end up using the exponential rule, the chain rule, the product rule. So there's kind of a lot going on here. The first thing that you want to be able to notice is that you've got like these two x variables that are multiplied together. And so in this case, we've got this expression here that has an x in it, and this expression here that has an x in it. And the reason I'm emphasizing that they have an x in it is that we can't just use that regular coefficient rule, which is, just if you have something in front of the x, like in this case is 7, you don't have to do anything special to it. You just leave it there and then take the derivative of x squared. But that's not the case for this problem. So for this problem, we have two different things multiplied together. So that means we need to use the product rule. So the product rule for this one, again, I was kind of mentioning what techniques I use to try and remember the quotient rule. I try and follow the same pattern for the product rule. So for that reason, like for the quotient rule, I always start with the denominator, which I kind of view as the second function. So I do the same thing for the product rule, although honestly for the product rule, the order does not matter because we're using addition instead of subtraction. So it doesn't matter which one you write first, but that's just for me to keep track of the two so I don't mix up with the quotient rule which one comes first. So I always start by writing the original second function, which in this case is e to the 6x, so I haven't done anything to it, I have not taken a derivative. But now I'm going to take a derivative. So I wrote e to the 6x, now I want to take the derivative of 5x squared. So the derivative of that would be 5, and then 2x to the 1 is the derivative of x squared. The product rule indicates plus, so I'm going to put the plus here, and then I'm going to just switch them around. So now I'm going to start by just rewriting that first function without taking any derivatives, so that would be 5x squared. And then I want to take the derivative of the second function, which is e to the 6x. So just some notes about, let me use a different color here. E to the 6x, well, the rule for e, it's perhaps one of the easiest derivative rules because the derivative of e to the x is just e to the x. If only all the rules were that easy, right? So we will use that exponential rule, but we're also going to use the exponential function rule, which is basically just applying the chain rule. So since we have something more complicated, in this case e to the 6x, instead of just an x as our exponent, we have 6x. That when we go to take the derivative, we first start by just taking the derivative as we normally would for an e to the x function, which is just e to the whatever, just rewrite it as is. But then the extra chain rule part is to multiply by the derivative of that exponent. So the derivative of this exponent, 6x, is 6. So I'm going to go ahead and write into our product rule problem here, e to the 6x times 6. So this is our derivative. We do want to simplify it though. So let me go ahead and try and simplify it. So we've got e to the 6x times 10x plus, here I can do some multiplication because I've got the 6 times 5 that I can multiply together. So I could say plus 30x squared e to the 6x. So I don't know, I didn't quite write them in the same order, so maybe I'll just do that now just to keep them consistent. So here's the derivative. So this is the derivative for the original problem. I do just want to show you something else to keep in mind, which is that you could factor it, and this problem just asked to take the derivative, so you do not, if you're just taking the derivative, you don't need to go any further than this. But later on you might be asked to do something like set it equal to 0, and if you do that, then factoring comes in handy. So I just kind of wanted to mention though, with a problem like this, yeah, you can look at the 10x and the 30x squared and factor, but you can also do the same thing, like there's an e to the 6x in common, so you can actually factor out an e to the 6x as well. So let me kind of write that out. So between the 10 and the 30, you would take out a 10. The x and the x squared, you would take out an x. And they both have an e to the 6x, so you could take that out also. And then in the parentheses, we'll write what we have left over. So it looks like everything in that first term gets factored out. So there we're just going to have a 1 left over, plus, and then just as a reminder too, is that when you're factoring, you're actually just dividing by. So what happens is you've got 10x e to the 6x divided by 10x e to the 6x, which is just 1. And then over here, divide, which would leave 3x. So that's another way to write the answer. Both would be correct derivatives.